Hi everybody. For the next little while, we're going to talk about arcs of a circle and how they relate to central angles and inscribed angles. Well, you should know all about central angles, inscribed angles, and how they relate to the arcs that they cut when we finish this little talk. To begin with, we'll talk about arcs in this first picture, arc AB, BC, CD, and DA. That's the arcs, the full arcs of this whole circle, huh? And it tells me that they're in a ratio of 1 to 2 to 4 to 5. I'm going to have to figure out the measures of those various arcs. If they're in the ratio of 1 to 2 to 4 to 5, and yeah, because they're the arcs of a circle, I know that they add up to 360. The degrees of arc will certainly add up to 360. We can rest assured that 1x plus 2x plus 4x plus 5x equals 360. Let's see what that brings us. So we got 3 and 7 and 5. I got 12x here, I think, all told, is equal to 360. And I'm happy with that. We'll divide both sides by 12 and figure out that x must have been 30. Now you bear in mind, one of those arcs must have been 30. I guess that was arc AB was 30 degrees. One of them must have been 2 times 30. That must have been arc BC was 60 degrees. One of them was 4 times 30. That would have been arc DC, I figure. 4 times 30, 120 degrees. And then 5 times 30 and 150. You got to check on those, be sure they add up to 180, but I'm pretty sure they do. 30 is 60, there's 90, and 120 is 210 more. Yeah, that's 360. So we know the measures of these several arcs, don't we? Arc AB, 30 degrees. Arc BC is 60. Arc CA, 120. And this is more interesting, arc CDA, from C through D to A, that's this 120 plus this 150. Whenever I got an arc named with 3 letters, it's going to be a major arc. That's a semicircle or more. And the sum of those two is 270, it seems. But it asked me for these couple of angles. Let's check those out. Angle DZB. D to Z to B. That's this one. And what you got to know is the central angle is the same as the arc it cuts. And this angle DZB cuts arc DB. And that arc is 150? I guess it was, huh? Plus 30, that should be 180. So that makes me think that angle DZB would be 180. I'm not really going for that. I think my picture's a little bit wacky. But if this was 150 and that's 30, that should be a straight, that should be a semicircle right there, and that should be a straight line. What about angle AZD? AZD? That's this little angle, huh? A to Z to D, and that's a central angle, and it should be the same as the arc it cuts. So I'm going to report that would be 150. I don't like the way that this came up to be 180, but if the arc that it cuts is 180, then it had to be 180 degrees of angle. Picture's not drawn beautifully. We'll get some more chances to see things like that. Circle Z, here we go. AB is a diameter. So I'm thinking there's a semicircle, ACB is a semicircle, and ADB is a semicircle. It talks about arc AC. I'm going to label what it tells me. AC is 6x plus 4. And CB, this arc, 8x plus 22. And I figure there's something we got to do with those couple of expressions to write an equation. Because this is a diameter, here we have arc ACB being a semicircle. The arcs of a full circle add up to 360. The arcs of a semicircle add up to 180. So our equation here ought to be that those things add up to 180. 6x plus 4 plus the other arc, 8x plus 22. Those ought to add up to 180. They're the arcs of a semicircle. Gathering like terms, we get 14x plus 26 equals 180. Let's subtract 26 from both sides. I got 14x. And 180 minus 26 is going to be 154. Let's divide both sides by 14 and see what we can do about that. I'm thinking 14 goes nicely there, huh? I think 14 goes into 154 11 times. So let's figure out about those couple of arcs. This one should have been 6 times 11. That's 66 plus 4. That'd be 70 degrees of arc, wouldn't it? And this one should have been 8 times that x equal to 11. 8 times 11 is 88 plus 22. That'd be 110, huh? And I'm liking that because I wanted these two arcs, this 70 and this 110, to add up to 180. So I can report those kind of answers already. Arc AC, 70 degrees of arc. Arc CB, 110. Now let's check out this one, ADC. That's a major arc from A through D to C, starting at A, going through D, and continue all the way until you get to C. That's nearly all the way around the circle, isn't it? It's everything except this arc AC. And since that arc was 70, this must be 360 without that 70. That'd be 290 degrees. I figure you could have added this 180 plus this 110, and that would have been the same thing. 180 plus this 110 would add up to 290 also. Arc CDB, from C through D, and it's terminating at B. If I start at C, go through D, and terminate at B. That's the whole distance around that circle, except this arc, that's 110. That must be 250. Probably another way we can look at that, though. If I would have added this 70 plus 180, that would have given me the same 250. So I can add up arcs like you would expect. Watch this. This is going to tell us about inscribed angles. In this circle C, arc DA is 150. What we need to be thinking of, since this was a diameter, here we have a semicircle, and this little arc would be important to us. I know these two arcs should add up to 180. That was going to have to be 30 degrees. And it asked me for the measure of angle ACB. ACB. What kind of angle is that one? Well, that's a central angle is what that is. And a central angle is the same as the arc it cuts. So our angle ACB must be 30 degrees. But watch this. If this angle is 30 degrees right there, check out this triangle that I'm shading right here. Mustn't it be isosceles? Yeah, because those radii got to be congruent, huh? And shouldn't these two angles add up to 30? Here's what I'm thinking. That's an exterior angle on the triangle. You can say that this angle is 150, the supplement of 30. Subtract 150 out of 180, and those two angles got to add up to what's left. And that these two angles would have added up to 30. So that makes this angle have to be 15 degrees, and this one have to be 15 degrees as well. A couple of things I ought to be talking about right here. Work with the angle ADC and find the measure of angle ADB. ADB, that's this angle. Yeah, that was that 15 degree angle, huh? Generally, how does one measure a central angle? This was that central angle. How did it relate to the arc that it cut? I'll tell you that a central angle is the same as the arc it cuts. Let's write that down too. Central angle equals the arc that it cuts. And we may do a proof of this other thing, but let's just get a look at what's going on right here. How does one measure an inscribed angle? And you may be wondering, what's an inscribed angle? An inscribed angle is an angle whose vertex is on the circle itself. This angle D, with its vertex on the circle, is an inscribed angle. Look at the arc that it cuts. Bring that ray out and bring this ray out. It cuts this arc of 30 degrees, and its measure is 15. How does that angle relate to the arc that it cuts? And it is true, what you generalize from here, that an inscribed angle is 1/2 of the arc it cuts. We're going to need to remember that. There's a lot of stuff that goes along with it. Inscribed angle. 1/2 the arc that it cuts. Now let's see if we can't put that to work. Here it talks about the arcs of a circle again. It talks about arc AB, BC, and AC. Now that's the full arc of a circle, and it gives me their ratio. I'm going to find some angles in a moment, but let's work with that ratio. Since these are the arcs of a circle, they add up to 360, and they're in the ratio of 3 to 2 to 5. I figure we could call them 3x, 2x, and 5x, and they better add up to 360 since they're the arcs of a circle. That gives us 10x, doesn't it? 10x equals 360. Divide both sides by 10, and like you're thinking, I'm thinking that x must be 36. Now let's go ahead and think about this. One of the arcs should have been 3 times 36. That'd be 108. I'm judging it by its appearances, but I think that's valid. We can do that. And one of them is 2 times 36. That'd make this one be 72. And one of them is 5 times 36, and that'd be 180. Hey, if this is 180 degrees, then this ought to be a diameter, huh? I'm curious about these angles now. I'm going to have to figure that stuff out. Arc AB, we figured that out to be 108. Arc BC, we figured that one out to be 72. And arc AC, that really should be named with 3 letters, but I don't have that opportunity. I'm going to call it 180. Whenever you have a semicircle or more, we ought to name it as a major arc. That should be with 3 letters, but we'll go with what we got. Now, what kind of angle is angle A? Angle A is an inscribed angle. How do you measure an inscribed angle? 1/2 of the arc it cuts. Angle A cuts this arc, CB. That's 72 degrees. Therefore, the measure of angle A is 1/2 of 72. That'd be a 36-degree angle, huh? Let's go for the measure of angle B. Now, this is an interesting thing. Look at the arc that angle B cuts. Bring out a ray and the other ray, and it cuts this arc of 180 degrees. If an inscribed angle is 1/2 of the arc it cuts, it's 1/2 of that 180 degrees. That'd have to be a 90-degree angle, wouldn't it? Kind of looks like a right angle to me. I'm thinking that fits. And then I'm going to care about angle C as well, this one. What arc does angle C cut? There's a ray here and a ray going that way. And it cuts this arc of 108 degrees. An inscribed angle with an angle with its vertex on the circle is 1/2 of the arc it cuts. Half of that 108 is going to have to make that be 54. Something you ought to check. Be sure that the 3 angles of that triangle add up to 180. Are those adding up to 180? I'm pretty sure they are. Let's play some more. Circle O, and a circle's named by its center. Arc ABC from A through B, terminating at C, is 240 degrees of arc. Makes me wonder about this small arc on this side, huh? Since the full arc is going to be 360, and this part, this major arc ABC was 240, that forced arc AC to be 120. I'm sure that's going to matter to us. And then we're going to figure out a couple of angles. Angle AOC. What kind of angle is that? Yeah, that's a central angle, isn't it? How do you measure a central angle? A central angle is this equals the arc that it cuts. If it cuts 120 degrees of arcs, that had to be 120 degrees of angle right there. What about angle ABC? That's the one I care about now. Well, that's an inscribed angle. It does cut the same size arc, doesn't it? And if it cuts an arc of 120 and an inscribed angle is 1/2 of the arc it cuts, that would have to be a 60 degrees of angle. Now I think that looks reasonably workable, doesn't it? Let's play some more. I got another page of notes I want to share with you. This is an interesting thought, this first thought thing right off the bat. Here we have a pair of concentric circles. Hey, what does it mean for circles to be concentric? These are concentric. Circles that have the same center are concentric. And it tells me that this angle X is 70 degrees. Give the measure of these 2 arcs. I should have had little arcs on them, but let me fix that now. Arc PQ, yeah, that'd be 70 degrees, huh? A central angle is the same as the arc it cuts, and arc RS is also 70 degrees. Ask me, is arc PQ and arc RS, are they congruent? I see they're both 70. What do you think? Is this arc congruent to that one? I gotta say they're not congruent. They are equal in measure, but they are not congruent. For arcs to be congruent, they must be in the same or congruent circles. Since these are in different size circles, no arc on the smaller circle could be congruent to any arc on that larger one. So no, they're not congruent. Not congruent, he says emphatically. Why not? Because congruent arcs must be in the same circle or congruent circles. Same or congruent circles. And since these circles are not congruent, those arcs cannot be congruent. Let's play some more. Circle B, this must be circle B, has diameter AC. I'm going to bear that thought in mind. That's a diameter, and arc DC is 60. It's good if I go around finding all the arcs that I could. I'm thinking if that one's 60, and this is a diameter, here's a semicircle. ADC is a semicircle, so arc AD has to be 120. We're going to figure out some angles in a minute. Let's see what I can do. First, it talks about angle ABD. ABD. What kind of angle is that one? Its vertex is at the center of the circle. That's a central angle. A central angle is the same as the arc it cuts. That angle had to be 120 degrees. What about angle A? Well, angle A's vertex is on the circle itself. That's an inscribed angle. An inscribed angle should be 1/2 of the arc it cuts. And angle A, you can see, cuts this arc of 60 degrees. So I'm saying that angle A's got to be 30. 1/2 of the arc that it cuts. Then it has to be about arc BDA. From B through D to A. That's this one. Now, I don't know if the arc that guy cuts. It doesn't come out, so I can't measure the arc that it cuts. But I do recognize that this is an isosceles triangle. At least isosceles, huh? In fact, it's kind of super isosceles, because that central angle is 60, and if these two sides are congruent, then these two angles would be congruent. Actually, if 60 went there, these would have 120 to share. They're going to be 60 apiece as well. That's an equiangular triangle out there. That's an equilateral triangle. So, measure of angle BDA. Oh, that's what it asks about here. Angle, I could have worked that same way here. This is an isosceles triangle as well. If angle A is 30, yeah, angle BDA is also 30. For the same reason as I was going through here. Then it asks about angle BCD. And we just figured out if this were 60 and this is an equilateral triangle, this would have also been 60. How about angle ADC? Oh, no, that's different from what I was thinking, from A to D to C. That's an inscribed angle. In fact, what arc does it cut? It cuts this large arc, doesn't it? All the way to there. And because this is a diameter, that's 180 degrees of arc, and that would have to be a right angle. There's a 90 right there. And I'm thinking, if this were 30, wasn't that angle, what do we think? Angle A had to have been 30, and this angle had to have been 60. Yeah, that would have to be 90 right there, and that's a big 30, 60, 90 triangle. Let's play some more. Going to work out with the arcs of this circle. I'm going to find the measures of some angles also. Arc AB, let me just get this data in place. 5x plus 10. Arc BC, 6x plus 100. Well, arc CD, this little arc is 50 minus x itself. And arc DA is 7x plus 30. We got to do something with those arcs. We got to give some kind of an equation. I figure the arcs of a circle add up to 360, don't they? So I'm going to rattle them off, just set that up. 5x plus 10 plus 6x plus 100 plus 50, minus x plus 7x plus 30 ought to add up to, the arcs of a circle add up to 360. Let's gather like terms on those x values. 5 and 6, there's 11x. Take away that 1, I'm back down to 10x plus 7. I got 17x, I think. And I have a positive 10. Gotta gather the constants. A positive 100, a positive 50, and a positive 30. Let's see about that. 110 and 50 more, that's 160. And 30 more must be 190. Adds up to 360. Now let's solve that little equation. I think it's going to come up nicely. Let's subtract 190 from both sides. I got 17x equals, and 360 minus 190 leaves 170, huh? Divide both sides by 17, and I'm thinking like you are that x is equal to 10. Let's go figure out about those arcs, if x is truly 10. This one would have been 5 times 10. There's 50, plus 10 would have been 60 degrees of arc. 6 times 10 would have been 60, plus 100 would have been 160 degrees of arc. Well, 50 minus 10 would have made this thing be 40 degrees of arc. And 7 times 10 plus 100, plus 30, excuse me, would have been 100 degrees of arc for arc DA. Now, let's find the measures of these angles. All three of these angles in this quadrilateral are inscribed angles. They have their vertex on the circle. Check angle A. Let's check out the arc that angle A cuts. AD is a ray and AB is a ray. It cuts arc BCD. And that arc is 160 and 40 more, huh? You have to sum those two arcs up, and that's 160 and 40 more. Those arcs add up to 200 degrees. So angle A must be a half of that. Must be 100 degrees. Let's find out about angle B. First, I'd look at the arc that it cuts. Trace the rays from angle B. It's at A, and it goes through C. So it cuts arc AC. It looks like it might be a minor arc. But how big is it? 140? Yeah, that arc's 140. So angle B would have been 1/2 of the arc it cuts. That would have been 70. Let's go for angle C. Same idea. Angle C has a ray that goes through D and a ray that goes through B. Cuts this arc DAB, or DB if it's a minor arc. What's the size of that arc? 160? And if that arc's 160, this angle ought to be 1/2 of the arc it cuts. Half 160 forces that to be an 80-degree angle. One more time, let's get the measure of angle D. What arc does it cut? One of the rays goes through C, one of the rays of angle D goes through point A. So we're looking at this major arc, ABC. How big is that major arc? This part was 60, this part was 160, that should be 220. And if an inscribed angle is 1/2 of the arc it cuts, that forces this to be 110. So I think I got all the angles in this quadrilateral. And you might be remembering that the angles of a quadrilateral got to add up to 360. I bet these do. I see 210 and 80 would have given me 290 and 70 more, adds up to 360. So I'm pretty happy, yeah. These angles of a triangle, of this quadrilateral, excuse me, adding up to 360. Let's go here and play with this too. TB is tangent to circle X at point A. I'm thinking right away, well, that's a right angle right there, because I know a tangent is perpendicular to the radius at the point of tangency. Goes further to tell me that arc AED, A through E, all the way to D, that's 230 degrees of arc. Now, if that's 230 degrees of arc, and I'm pretty sure that this is a diameter, so this must be a semicircle, that is AEC is a semicircle. There's 180. What does that leave for this place? Must be 50, huh? Because here's 180 and 50 more, giving me that 230 that is arc AE or ACD. So I take that arc to be 50. And you might be thinking about arc DA as well. We're going to need it. Again, if this is a diameter, there's a semicircle. C through D to A is a semicircle. Got to add up to 180 degrees with those arcs. So this would have been 130. Now, let's get a couple angle measures. Here we have an inscribed angle. How do you measure an inscribed angle? Angle CAD. An inscribed angle is 1/2 of the arc it cuts. That'd have to be 25 degrees, wouldn't it? Now, just thinking ahead a little bit, if this one's 25 right there, and these two angles add up to 90, what would this angle have to be? Well, 90, and take out that 25 from 90, that had to be 65 degrees, huh? Now, let's look at this angle, formed by a tangent and a chord. And I might ask you, how do you measure that angle anyway? Look at the arc that it cut. It cut an arc of 130, and its measure is 65. Yeah. How do you measure an angle formed by a tangent and a chord? It's 1/2 of the arc it cuts. I would go back to, if the vertex is on the circle, like a inscribed angle is, it's always going to be 1/2 of the arc it cuts. And this angle has its vertex on the circle. In it again, it is 1/2 the arc it cuts. You might make that note, that an angle formed by a tangent and a chord is 1/2 of the arc it cuts. One more thing for us to look at. Check out the inscribed quadrilateral ABCD. To be inscribed, its vertices must be on the circle. Angle A is 110. As soon as you tell me that angle's 110, I might be thinking about this arc DCB. Let me just make a note about it over here rather than screw up my whole page. This angle A, which is measure 110 degrees, cuts this arc DCB. An inscribed angle is 1/2 the arc it cuts, so that big arc must be 220. Hold that thought. Angle B, this one, is 70 degrees. So that ought to tell me about an arc as well. What arc does this angle B cut? It has a ray that goes through C and a ray that goes through A. Yeah, it cuts this arc AC. And an inscribed angle, that one is 70, is 1/2 of the arc it cuts. So I know about this big arc, A to C, must be twice 70, must be 140. Now, let's see what we can do with that. How big is angle C? Now, I'm going to have to figure out what arc angle C cuts. And if I keep my act together, I think I can make that happen. I did know that angle DBC, let me get that right, was that DBC? It was 220. I don't think I wrote that well. Let me look through some stuff here. If angle A is 110, then that should have been DCB. DCB, my error there. DCB should have been 220. And if that arc is 220, DCB, what about this arc DAB? Well, the arcs of a circle got to add up to 360. If this part is 220, then this would have to be 140. Now, can you tell me about angle C? Doesn't it cut that 140 degrees of arc? Yeah, it does. It's 140 degrees. Excuse me. Doesn't it cut that 140 degrees of arc? And isn't it an inscribed angle? So isn't it 1/2 of the arc it cuts? It is 70 degrees, isn't it? That's where that one ought to be. Now, let's see if we can get angle D as well. And what I'm really thinking about was, what about this angle B? Angle B cut this arc AC. And we knew that that arc had to have been 140. If that arc is 140, then its complement, everything else, was going to have to be 220. Because 140 and 220 add up to 360. And if that's 220, how about angle D? Does it cut that 220 degrees of arc? It does, so it has to be 110. I might have to make a video about this, but something I know about a circle and an inscribed quadrilateral. Let me just show you something about this right quick. Any inscribed quadrilateral doesn't have to be a square. Let's look at a pair of opposite angles. Isn't it true that this angle would be 1/2 of this arc? And this angle would be 1/2 of this arc. These two angles would add up to 1/2 of the 360. Therefore, these two angles are supplementary. They add up to 180. And that's a theorem that we may need to prove somewhere along the line, but I can guarantee it's true that opposite angles of an inscribed quadrilateral are always supplementary. These should be supplementary. Those should be also. I think it worked out just fine over here. When angle A was 110, what about angle C? That's the opposite angle. Angle C was 70. When